hopefully you can watch the video and get the credit. All right. So, we ready? All right, so again, we're on page 83. It says a random sample of 25 cheeseburgers. Oh, they had me at cheeseburgers. Ordered at a specific fast food restaurant, average 820 calories with a standard deviation of 35. We wish to use a confidence interval for this data. So, all right. So the first one, they say they want to find us a 90% confidence. Okay. So how am I going to find the 90% confidence that goes with this?
Do that one equation.
Yeah, what is it called? What was it called? Isn't it inverse norm? Or wait, I gotta bring it up. I gotta look. I said the wrong one.
Yeah, I like to think it's inverse norm for the critical P.
Oh, you're the best. So, go here.
We have to use charts, right?
Hang on. Oh man, what's going on with my computer, dude? There we go. All right. So 90% confidence. You find 90 on this T distribution table. Now you gotta make some more copies if you need another copy. Okay, so being we have 25 burgers, what number should I use?
24.
Yeah, use 1 minus it, so we're going to use 24. So I'm going to go 90%, go down to 24. 90% looks like 1.711. Sound about right? So we get that based on our table.
Wait, how did you do that again?
So on our table I had given you the other day,
Yeah.
you find 90%.
Yeah.
And then they had 25 cheeseburgers, so we're going to use 24 because degrees of freedom is always one less. So you find 24, move over to you find the 90%, you find the 1.711.
What chart? Thank you.
Sure.
Wait, we get to use that on the test.
Sure.
Wait,
Well, Swanee has to have the whole thing memorized, but you can use it. All right. So,
so it's not the inverse norm?
no, because we're using a T distribution. You might have an inverse T distribution on the calculator, but not all of them have it. All right, so find the critical of 90% confidence, explain what the value. So 1.711 standard deviations from the mean captures 90% of any bell curve. Okay, that's basically what it is. So what that means, again, we keep drawing a normal distribution. If I went out 1.711 standard deviations from the mean, this region here would be 90% of the area under the curve. That's all it is. Okay? Calculate the margin of error at a 90% confidence. What do you think?
I just do the critical value times the standard deviation over the point estimate.
So critical value, standard deviation over the value, the number.
The number.
Okay, so 1.711.
Yep.
Standard deviation is 35 over 25 cheeseburgers. Right? So that's going to come out to 11977, I believe. So that means what this value means is we are 90% confident that we would be within 1.711 of this. So if I had this and I did plus or minus the 1.711, that would create a confidence interval. I'm not going to necessarily do the arithmetic. Actually, we have to do that for 3, so we might as well do it. So this is the answer for 3. This goes to 808.03, 831.3, 88.97. So basically for number 2, we are 90% sure that if we recapture our information that we're going to fall somewhere in there. Okay, and that's our confidence interval. And interpret the meaning of this confidence interval in the context. So we're 90% confident that the average calorie count of cheeseburgers is of this particular restaurant is between 808.03 and 831.97. Okay. Not too bad. Agree?
Yeah.
Okay, so next one. Ran a sample of 10 homes in the Sunnyside neighborhood in Miami. I don't know if this is real or not. Showed an average home value of $410,000 with a standard deviation of $100,000. Holy cow. So average $410,000, standard deviation of $100,000. That seems pretty broad, but okay. So produce a 95% confidence interval with that. All right, so I'm going to go 410,000 plus or minus. Now we have to figure out what this value is here. Okay. So we have 10 homes. What number am I going to use?
100,000.
Nope. If I have 10 homes, what am I going to use for my degrees of freedom? 9. Okay. And we wanted a what? 95%? So we find 95% and we go down to 9. Looks like 2.262. Okay. Times the $100,000 standard deviation over our sample of 10. So the sample stays the same size. When I do the degrees of freedom, it becomes 10 minus 1. That's why we use the 9. Okay. That's just statistically what they have found that it works. So if you do this math, it should come out to 338,469 to $481,531. Okay, so that's for a 99% confidence interval. 99% confidence makes more sense. 100,000. So if you're talking about a $400,000 home, $410,000 home, 100,000 is pretty big. That's going to capture a lot more area. If this number was smaller, our area that we're capturing is smaller and smaller and smaller. If that number is larger, it means because that standard deviation is so big, you're going out to 99.1, 99.2, keeps going. So what this means is, in general, what do problem 5 and 6 mean? As the confidence level rises, the interval also gets wider. Okay, they kind of say that you don't say the interval decreases for whatever reason. I guess you'd say it gets less wide. I don't know why you wouldn't say that it would decrease. So as the confidence interval gets bigger, as this gets larger, the area we are looking at is wider. And again, that's dealing with the normal curve. Let's pretend I can draw a good normal curve still. So the area that you're getting, you're approaching the 100%. 99%, you're talking about 0.5% is on each end of the tail. Okay, so you're talking about a very small number of things. We've all probably driven through a neighborhood where you might be driving through a neighborhood that is specific, and I'm not gonna, I'm not making fun of this neighborhood. I'm just saying it is what it is. Y'all know where Pirates Cove is? Okay. So that neighborhood around there is in transition. Yeah. Meaning people are buying the 2-bedroom, 1-bathroom house that's about the same square footage as of this room. They're knocking it down and they're putting a Cadillac there for a house. So you can still drive through the neighborhood and you see this little 800 square foot home, and then you have this home that's like 2 lots wide and looks like something that could be in Cherry Hills. Okay, so Those kind of things kind of mess with it. But when I coached my daughter in soccer from, oh my gosh, kindergarten through 8th grade, so 9 years worth of coaching, we spent a lot of time over in that Pirates Cove area, because that's where United Soccer always had their stuff, which was great. But there's definitely times where it was like, oh my gosh, they have some homes here that don't look like they fit. Do you want to know what I heard?
It's like every dream house.
You want to know what I heard about some of those houses? Okay. So we have this green leafy substance that's now legal here in Colorado. Y'all catch my drift? Yeah. For a long time, the federal government wouldn't allow these green leafy selling places to put money in an FDIC approved bank. So those green leafy places need to take their money and figure out how to make their money, be safe. So they go into a cash deal on a junky home, smash it down, build up some big old nice home, turn around, parlay their money and sell it for more than what they invested, and then they could put that money in the bank. So the real estate market was a laundering scheme for marijuana.
That's actually kind of smart if you think about it.
I know. There were realtors that they would not sell anybody a house. They were working directly with the pot shops, saying, hey, do you have another house? Yeah, I found this little place hasn't been lived in for 12 years, and there's more rats and mice in there than anything else. How much does it go for? It goes for $28,000. Okay, here's $28,000. What are we going to build there? I have an idea for a 6,000 square foot home, 4-car garage, and swimming pool. Every counter in there is going to be made of marble. How much is that going to cost me? $1.2 million. Okay, here you go. How much can we sell for? $1.8 million. Okay. I kid you not. Crazy. But, they figured out how to make the system work. And of course, then you get the federal government going, well, shoot, what are we supposed to do now? It cracks me up. They don't think so. I don't know. Yeah. But my understanding is a lot of those types of things had been taking place because, and I'm not saying it's right or wrong. I'm just saying that's what a lot of times was happening. And there were some of those neighborhoods that were in older areas, maybe not as affluent areas, that all of a sudden the demand goes up for. Here you go, Gio. You can sit in comfort over there. That's your chair. That's your tardy chair. Okay.
Party chair, I guess.
Yeah. Yeah, I hope you learned your lesson to sit in a comfy chair. Whoa. All right. So, where are we at? Did we get done with that one? Are we on number 8? Okay. Educational researchers wish to find the average ACT score of students at a particular school. A random sample of 10 students produced an average ACT score of 20.2 with a standard deviation of 6.8. So our sample is 10 kids. We have an average of 20.2 and a standard deviation of 6.8. Okay. Explain briefly why a T interval is used and not a Z interval. This is key. Why is a T being used and not a Z? Okay, that's one part. Why would I use a T table and not a Z table?
Under 30.
You're absolutely right.
Let's go.
Yeah, baby. Yeah. We're talking about 10 people here. We're trying to make a valid assumption off this. When I have a small sample, I want to use the T table instead. Now, you can use a T table for large samples. And in fact, if you compare that table I gave you, there is a table very similar to that would be for the Z scores. And after you get to a certain sample amount, the t-table distribution and the z-table distribution become the exact same. But the main thing that you're doing there, yes, you do have the sample standard. You have the overall standard deviation, but because I have a score, I'm only using 10 people. If you look at your degrees of freedom, it goes all the way down to 1, which means you could have a selection of 2 items. Your degrees of freedom make it 1. I mean, that's pretty broad. Okay, so the standard deviation, it was used here. It was obtained from the sample, but you were also, because you have a small sample size, you want to use that. Calculate an interval at 50% confidence. Well, Stirrup made a boo-boo. Sorry. So they want a 50% confidence interval. Let's change this to 60% because your t-table doesn't have 50%. Sorry, I got the B version of it. I didn't get the A version. All right, so if I wanted to create a 50% or 60% in this case, degrees of freedom would be 9. So you're looking at 0.883. If you change this, degrees of freedom would be at 9. So you're going 0.883. So what that means, in order, so again, realize this, friends, I'm changing this 50% and making it 60%. So our confidence interval would be, excuse me, 20.2 plus or minus the 0.883. Is that right? Or no?
Yes.
Yep.
How do we get the 0.883?
So I changed, it asked for a 50%.
Yeah.
I didn't have 50%, I think, so I went to 60. So 60 degrees of freedom 9 is 0.883.
Oh, yeah, that's right.
So, am I good?
Yeah.
Good.
Yep, 0.883.
Okay. Somebody have a calculator. What is
Um,
0.21?
isn't it-
I can't do it in my head.
Hold on, wait,
20.2 plus 0.883.
hold on, don't you have to find the margin of error first?
Yeah.
Hold on.
Yeah. So what goes next?
I did 0.883 times 20.2 over the square root of 10.
Square root of 10. There we go. All right. So what do we get to then?
5.64.
5.64?
Yep.
There we go. So then we're going to go, is that 25.84?
Yep.
I won't put it in the wrong spot. 25.84.
14.56.
14.56.
Yeah.
Okay. So, get too many dots there. All right. So that's pretty broad spectrum as far as the ACT score. One, we're talking about 60%. Also, other things that are holding into validity is we're talking about 10 people we're doing, so degrees of freedom. So we are 60% confident that the ACT score would be from 14.56 to 25.84. Considering the answer to number 10, explain why the confidence level of 50% is not used often. Okay. So they're saying why would, so you could say this easily. Well, the 50% is not used often because one's not showing up on the t distribution I gave you. But you're also, if you were to use a 50% thing, you have a 50% chance of failure. Okay, so think about that. Or in our case, we use the 60%. We have a 40% chance of failure. Okay. Calculate a 99.9% confidence interval. Okay, so we want the 99.9%. Our degrees of freedom is going to be 9. All right, 99.9, 9 degrees, 4.780. Is that right? Okay. So what are we going to do from there? Find the margin of error. So we have our this plus or minus what? Oh, wait. I went the wrong way.
Yeah, if you times 6.39, wouldn't it be the same?
Yeah. 6.39.
Yeah. And
Did you already take into account?
yeah, because wouldn't it be the same?
Oh.
Wouldn't it still be 20.2 over?
Yeah.
Okay, so yeah, 6.39. I got 30.5.
99% degrees of freedom. 4 points. Is that what you did?
No.
No. Where were we at? 6.39 times.
I did 6.39 times 4.7. Because, so 6.39
Is the standard deviation divided by root n?
yes.
Okay. So what do we get here?
So then after that I got 30.5.
30.54.
Yes. And then it would be 20.2 plus or minus.
20.2 plus or minus that? Oh my gosh.
So then, yeah, I didn't know if I did this right because I got a negative.
No, I think the negative should happen.
Okay, so then negative 10.34 and then 50.7.
Yikes. Okay. So a couple things that jump out at us. We're still talking ACT score, right? Friends, am I going to get a negative 10.34? Am I going to get a 50? No. Highest score is what, a 36?
Yeah.
So we have a 99.9% chance that we're going to, there's only a 0.1% chance that we fall outside of it. How does that happen? I wouldn't. Okay, considering answer number 10, explain why the confidence interval. Okay, we did that. Interpret the confidence interval. So we are 99.9% sure that we're going to fall in there. So someone's got a chance that they fall outside of it. Considering your answer to 13, explain why the confidence interval of 99.9 is not used often. Think about the area on the curve being 99.9%. You're capturing everything. I mean, the 0.1%, which is 0.05% that's at the tails. I mean, there's 0.05 down here. There's 0.05 over here. That's tiny. Okay, so that's why it becomes kind of a worthless test. So, think of this. I already heard one this morning on my way into work. I heard a campaign video already. Campaign videos are getting worse than Halloween. You know, like when you walk into Target in August and they got Halloween stuff out already? You wait. It's going to be June now. Because they're going to try and follow the campaigns. All right, so that little tiny small print at the very bottom saying, hey, margin of error is this. Keep an eye on that 99.9%. Keep an eye on the 50%. You don't want any of those. That's kind of a goofy way to think. All right. So can I start 510? If you are here, I'm putting the points in for 5.9. Who's not here? Raise your hand if you're not here today. Here. Who else is not here? George? Are you kidding me? What page was it? That was 5-9. All right. All right. Let us lecture a little bit about 510. I'll only start this. I won't get done with it. Don't worry. We got time. We got time being that we're so behind. It's not even funny. All right.
I still need the chart.
Yeah, hang on to the chart. You probably won't need it for today's, but hang on to it. Don't dispose of it. So 510, the meaning of a confidence interval. Meaning of a confidence interval. So, my friends, I'm on page 19 of our notes. What does it really mean to be 95% confident of something? So let's assume we collect a random sample of people who visit a movie theater and create a 95% confidence interval estimating the average amount spent on concessions. Let's assume that the interval is 6.25 to $8.50. I don't know what movie theater these guys are going to, but I'd say the price of a movie theater is pretty high. So, go to the Elvis. Is the Elvis still open? Oh, sweet. All right. So, this means we are 95% that the true average amount spent on concessions is between. So, the true average is within this confidence interval. Okay? So, the true average. Now, some people say the true average is halfway in between the two. Careful with that. What the 95% confidence interval is, I'm 95% confident that if I keep selecting information, that my average will somewhere fall between those numbers. It doesn't have to be directly in the middle, but I'm 95% confident. So the true average is a fixed value. It exists, but it's unknown to statisticians. And if it's unknown to them, we all don't know it then. Our hope is that our confidence interval captures this value. We never actually know for sure because the population mean, the true average people spend on concessions in this example, will almost always stay hidden from us. Okay, imagine 100 different researchers found random samples and created their own confidence intervals estimated on average between the people spent on concessions. We would expect 95% of those confidence intervals of the 100 that were there, 95 of them, would successfully capture the true average, and approximately 5 would not. The statisticians who found the random sample and failed to capture the population did nothing wrong. It simply was the nature of random sampling. Occasionally it produces an unusual result. So that graph is kind of weird to look at. But what that graph basically is it's supposed to look something kind of like this. And then you have this dotted line that goes in there. So each one of the vertical lines that you can't really see is basically a different random sample. So with a 95% confidence, you would have 5 of these that would fall outside of the pink. And you would have 95 that fall within the red. I realize I didn't draw 100 reds, but only 5 don't fall into that. Okay? The pink line is where the average, we're thinking we're going to capture it. Consider the graph below of many confidence interval, all attempting to capture the population mean of 5. As you can see, most confidence intervals successfully capture the population mean of 5. Those in red, it's indicated by the dots, so mine are not the dots, failed to capture the population mean. So some intervals are wider, some are narrower. So that's what you're trying to capture. Okay? So 95% confident means 95% of every 100 samples will produce confidence intervals that capture the population mean. It is expected some of these intervals will fail to capture the population parameter, and this akin to rolling 2 dice. It is expected that every so often the unusual result of rolling double sixes will occur as a byproduct of randomness. Okay? So bringing the dice in. So I think I will finish teaching this tomorrow, but I think you could start on page 85 and try 1 through 7. Good night.